Okay, example 3. Can I strongly suggest, this is a you-do example, that you write this down, rewind the video to my full solution for example 2, and have a go yourself before I go through the solution in a second. Okay, so I'm hoping you had a go yourself. Let's go through the full solution. I'm going to define this as AX equals S, and I'll do my working here. It means that A inverse AX equals A inverse S. So I've missed the A inverse there. Which means that X equals A inverse S, which means that X is equal to A inverse S. So I just need to work out A inverse. Now this is going to be the same every time, but it's really important to continue to show our working. Now first, I'm going to write down that A is equal to 2, 5, 1, negative 1. And the determinant of A is equal to 2 times negative 1 plus 1, or not plus, minus 1 times 5. And this is equal to negative 2 minus 5 is negative 7. So A inverse is 1 over, or negative 1 over 7 times by negative 1, negative 5, negative 1, 2. There's my little swaps around. A and D get swapped, B and C get made negative, and I'm going to leave it exactly like that. And then I get this. A inverse S is equal to negative 1 over 7, negative 1, negative 5, negative 1, 2, times S, which is 6, 2, 6, 2, negative 1 over 7, negative 6 minus 10 is negative 16, negative 6 plus 4 is negative 2, and I've got negative 1/7, so it becomes 16 over 7, 2 over 7 is my solution. And of course, I could run through and check that now quite easily if I needed to. So have a look at that, and we can now define A equals 16 over 7, or 2 and 2/7, and B is equal to 2/7. Okay, so that's example 3. Let's have a quick run through example 4. Now, I almost didn't put this in a video, but decided it's worth talking about. But I want you to understand, again, this is a little bit tricky, and if you haven't taken the time to consolidate from the example 3 methods, maybe this won't make too much sense. But we're linking back to the start of the video where we have 0, 1, or an infinite number of solutions. So we're talking about developing an example that generates an A that is not invertible. What does this mean? So I'm going to do this backwards. I'm going to say, well, let's let A equal something not invertible. And my 12 has got lots of factors. I like 12. So let's do 3, 6, 2, 4. Because this means that the determinant of A is equal to 3 times 4 minus 6 times 2, which equals 0. And therefore, it's a non-invertible matrix. And that's what we're looking for. Okay, so I'm going to set my equation up with these coefficients. 3x plus 6y equals, and 2x plus 4y equals. Now I'm going to do a couple of cases. The first one I'm going to do is equals 12 and 8. The second one I'm going to do is 3x plus 6y equals negative 4, and 2x plus 4y equals 7. Now what I want you to see here is that because we set up a non-invertible matrix, the coefficients there and the coefficients there are actually linearly the same. There are half as many x's as y in both cases. And in fact, I could divide by 3 and then divide by 2. And I could do it over here too. So divide by 3, divide by 2. And over here I get, we'll call this 1 and 2. We'll call this 1 and 2. I get x plus 2y is equal to 3. And then I get x plus 2y is equal to 3. So we actually have the same equation. And then that looks like this. If I sketch it, I get x plus 2y. I don't know what it looks like exactly, but that's the first one. And that's the second one. There's an infinite number of solutions. And when we say infinite number of solutions, I can pick any x. If x is 3, then y is a half, and that works in any case. And so 3, x equals 3, y equals a half, which is clearly not on here, is the solution. Over here, if I divide by 3, I get x plus 2y equals 4/3. and then I get dividing by 2, x plus 2y equals 7 over 2. Now we have a contradiction, because if I subtract these equations, I get 0 equals 4/3 minus 7 over 2, which I can't be bothered doing, but it's something about 2 and a bit, 2 and a 6 maybe, and that's a problem for us, because 0 can't equal some other number. So in this case, what we have is one line there and one line there and 0 solutions. So there's two things that can happen when we're dealing with a non-invertible. If we have an invertible matrix, we have a single solution. If we have a non-invertible matrix, then we may have an infinite number of solutions or 0 solutions. And this process will be important later on. So that's the end of video 11. Hopefully that wasn't too onerous. It was a bit of a big one, but you can see there that the points are important and you can finish your work on that now. All the best.